Hey everyone, my name is Sabrina Isaac Berry from Berry Science Lab, and today we're going to be talking about a two spring or a one spring system with two masses. So you have M1 here, you have a spring, and normally you would expect another wall to be on the other end, but instead we have a smaller mass, M2, and neither of them are fixed. So let's say the spring has rest length L, and M1 has been displaced delta x1, and M2 has been displaced by delta x2. Now we find the equations of motion of these two bodies. Now, what's the Lagrangian in this case? Well, it's always the kinetic minus the potential, which is half m1 x1 dot squared plus half m2 x2 dot squared, and then minus the potential. And realize the potential is going to be, there's only one spring, so the potential is going to just be half kx squared. But what is x? Well, that's going to be x1 plus x2. As you can see, it's going to be the sum of their displacements. Well, if you look at it another way, actually, it's more x2 minus x1. Why? Well, think about it. When m2 goes this way, it adds to the length. When m1 goes the same way, it subtracts from the length, just like this. If m2 goes this way, it subtracts from the length. If m1 goes this way, it adds to the length. So as you can see, it should have something like this. So now what are we going to do? Well, we introduce L. Wait, no, we don't introduce L. Sorry, what am I talking? We introduce the Euler-Lagrange equation. And plug in. What do we get here? Well, partial L partial x1 in this case is going to be minus 1/2 k times 2 x2 minus x1. Oh, and actually the minus comes out because this is negative. Is equal to x1 m1 x1 double dot. And if you want evidence, this is just d dt of m1 x1 dot, which makes m1 x1 double dot. Then, on the other side, erasing this, we have half 2k minus 1/2 2k x2 minus x1, and the second minus doesn't come out because x2's coefficient is positive, and that's equal to m2 x2 double dot. So now, what do we do here? Well, we first divide through by m1, and here by m2. And now you'll notice we can just subtract these. And we get x2 double dot minus x1 double dot is equal to minus k over m2 x2 minus x1 minus k over m1. Remember, we're subtracting a positive, x2 minus x1. Hence, you get minus k over m1 plus k over m2 times x2 minus x1. Now we introduce, let's just call it x. X is just going to be x2 minus x1. And what's that going to give us? X double dot is equal to minus k over m1 plus k over m2, which I guess I can also rewrite as k times m1 plus m2 over m1 m2 multiplied by x, just x. I was going to say x2 minus x1, but then I realized I should have cut off the sentence. So what do we have here? Well, we try the ansatz solution, x is equal to e to the rt, which is usually the culprit whenever you have x times constant is equal to derivative of x, or nth derivative of x. And indeed, we realize that that makes r squared e to the rt is equal to minus k m1 plus m2 over m1 m2 e to the rt, which allows us to cancel these terms out and gives us just this. So r is equal to the square root of this times I, which makes e to the I square root of k m1 plus m2 over m1 m2, and the only part of this that has meaning is the real part, and the real part of this can be, oh wait, remember, there can be an amplitude added onto this as well. Arbitrary amplitude cosine of the square root of k m1 plus m2 over m1 m2 t by Euler's theorem. So this is the value of x. But that still doesn't tell us anything about the values of x1 or x2. So what do we do about that? Well, we have now that x1 double dot is equal to k over m1 x. So we plug in what we got over here. And we go back and say this is ka over m1 multiplied by cosine k. You know what? I'm just going to write this as omega because I'm done with this. I'm done with writing this so often when it's so painful.
Is there any chocolate?
Yes. Chalks don't run out that quick. So you get this. And so that's relatively simple to integrate twice, right? And you get no, this would be cosine minus. Yeah, that looks good. And technically there can be a polynomial term or two here, but in actuality, as we know, that doesn't happen. So I'm not going to bother adding it. And we get something like this. Now similarly, x2 just ends up being x, wait, no, this would be x2 minus x1. x2 is just, wait, let me, hold up a second. I need to think. Yeah, that's right. x2 is x plus x1. So x is this, and x1 is this. So x2 naturally is going to be k minus, a minus ka over m1 omega squared multiplied by cosine omega t. And now you really,
it's getting crowded. It is around.
Yeah. And now you really start thinking it through, and you realize that, wait a minute, x2 is supposed to have what amplitude? x2's amplitude from its equation over somewhere. Where was it? Oh, sucks. This is here. Right? Yeah. This should be correct. Okay. So this equation over here tells us the value of x2 because we can just integrate twice. And what do we get? Because this is x. Well, this gives us minus k a over m2 omega squared cosine of omega t, which actually allows us to find this a over here. We get a minus ka over m1 omega squared is equal to minus ka over m2 omega squared. So, oh wait, you're forced to divide through by a. That sucks. Oh well. So, I guess a can be arbitrary, and it actually just depends on the initial conditions, delta x1 and delta x2. So finally, what did we get? Well, we got x1 is equal to, oh god, minus ka over m2 multiplied by m1 m2 divided by k times m1 plus m2, which, canceling out a bit more, gives us what? Minus a m1 over m1 plus m2 multiplied by cosine of omega t. And what about x2? Well, that's just going to be making an educated guess. A m2 over m1 plus m2 cosine of omega t. Which means both of them are going to oscillate with an amplitude that we can only know by taking the initial conditions. Oh, might as well. If t is equal to 0, cosine of 0 is 1. This disappears. A m2 over m1 plus m2 is equal to delta x2. Great. So that means A is equal to delta x2 times m2 over m1 plus m2. Doesn't matter. So you get a m2 over m1 plus m2 cosine omega t, which is similar to delta x2 cosine of what's omega again? The square root of k times m1 plus m2 over m1 times m2 t. And the same thing happens for x1. So at the end of the day, what do we have? This is going to oscillate with amplitude omega in this direction. This is going to oscillate with this is going to oscillate with frequency omega in this direction. This is going to oscillate with the same amplitude a and the same frequency omega, and no, it's not the same amplitude. This is going to oscillate with some amplitude delta x2. This is going to oscillate with some amplitude delta x1, and they're going to oscillate with a shared frequency. Omega is equal to the square root of k times m1 plus m2 over m1 m2. So now, just to summarize everything.
First, give an introduction and 10 seconds.
All right. So, okay. Hi everyone, my name is Saborno Isaac Berry from Berry Science Lab, and today we're talking about two bodies attached to the same spring. So right here, what system do we have? Well, it's M1, M2, both connected to this spring of length, well, rest length L, but it's been stretched by delta x1 in this direction and delta x2 in this direction. So what does that give us? Well, we take the Lagrangian, the kinetic energy minus the potential energy, we expand that out, then we plug it into the Euler-Lagrange equation, which I've unfortunately erased. But then we use a little bit of two-body mechanics. We substitute in x, which is x2 minus x1, as you can see from over here. And eventually we get from these two equations, x2 double dot minus x1 double dot, this constant times x2 minus x1. We plug that in and get this for x, and of course we try the Ansatz solution, which allows us to plug that in and get this value for x's motion. So then we apply that to the differential equations that we had before, and suddenly they become very solvable because before they were k over m1 x2 minus x1. Now we just plug in x. We already know the value of x, so we just integrate twice and get this. And the same thing for x2, which gives us this solution for x1 and this solution for x2.